Hello there, and welcome. Tonight, we're going to explore one of nature's most spectacular phenomena together, a light show that dances across the skies of the southern hemisphere with colours that seem almost impossible. We're talking about the Southern Lights, or as they're scientifically known, the Aurora Australis. While their northern counterpart often steals the spotlight, these southern curtains of light are equally mesmerising, equally mysterious, and equally worth understanding. As we journey through the science and beauty of this extraordinary natural wonder, let your mind drift with the gentle rhythm of facts, each one a soft step deeper into relaxation. There's something wonderfully soothing about learning while you rest, letting knowledge wash over you like waves on a distant shore. You don't need to remember everything. Just let the words flow past like the auroras themselves, ephemeral and beautiful. Now, before we begin, please take a moment to like and subscribe, but only if you genuinely enjoy what I'm doing here. Also, leave in the comments where you're tuning in from and what time it is there. It's great to see how these videos connect people from around the world. Now get comfortable and let's begin. First, let's establish exactly what we mean by the Southern Lights. The Aurora Australis is the Southern Hemisphere's version of the Aurora Borealis, and the name itself tells us a lot. Aurora was the Roman goddess of dawn, while Australis simply means southern in Latin. So we're literally talking about the southern dawn, which is quite poetic when you think about how these lights illuminate the night sky. The phenomenon occurs primarily in a ring-shaped zone around the Antarctic region, and this ring is called the auroral oval. It's not a perfect circle, and it shifts and changes shape depending on solar activity, but it generally hovers around the magnetic South Pole rather than the geographic South Pole. What causes this spectacular display? The answer lies in our relationship with the Sun. The Sun constantly releases a stream of charged particles called the solar wind, and this wind travels through space at speeds of around 400 kilometers per second. When these particles reach Earth, they interact with our planet's magnetic field, and this is where things get interesting. Earth's magnetic field acts like a shield, protecting us from most of this radiation, but it's not perfect. The charged particles, mainly electrons and protons, get funneled along the magnetic field lines toward the poles. As these particles descend into our atmosphere, they collide with gas molecules, primarily oxygen and nitrogen. These collisions transfer energy to the atmospheric gases, exciting their atoms to higher energy states. When these atoms return to their normal state, they release that excess energy as light, and that's what we see as the aurora. The colours we observe depend on which gas is being excited and at what altitude. Oxygen produces green light, the most common aurora colour, when it's excited at altitudes of around 100 to 300 kilometres above Earth's surface. This green glow is what most people picture when they think of auroras. But oxygen can also produce red light when collisions occur at higher altitudes above 300 kilometres. These red auroras are less common and often appear at the tops of very tall auroral displays. Nitrogen, on the other hand, gives us blue and purple hues. Blue light comes from ionized nitrogen molecules, while purple comes from neutral nitrogen. The specific mix of colours in any given aurora depends on the altitude of the collisions, the density of the atmosphere at that altitude, and the energy of the incoming particles. Have you ever wondered why the Southern Lights appear in an oval shape rather than directly over the South Pole? The answer has to do with Earth's magnetic field geometry. Our planet's magnetic poles don't align perfectly with the geographic poles. The magnetic South Pole is currently located off the coast of Antarctica in the Southern Ocean, and it's actually moving. The magnetic field lines converge at the magnetic poles, creating these zones where the solar wind particles have easier access to the atmosphere. The auroral oval typically sits about 3,000 to 6,000 kilometers away from the magnetic pole, and its size and position vary with solar activity. During intense solar storms, the oval can expand significantly, bringing auroras to lower latitudes where they're rarely seen. Speaking of solar storms, let's talk about what triggers particularly intense auroral displays. The Sun goes through an 11-year cycle of activity, moving from solar minimum to solar maximum and back again. During solar maximum, the Sun's surface becomes more active, producing more sunspots, solar flares, and coronal mass ejections. A coronal mass ejection, or CME, is essentially a massive burst of solar wind and magnetic fields rising above the Sun's corona and being released into space. When one of these CMEs is directed toward Earth, and it typically takes about 2 to 3 days to reach us, it can trigger a geomagnetic storm. These storms compress Earth's magnetic field on the side facing the Sun and stretch it out on the opposite side, creating conditions perfect for spectacular auroras. The intensity of auroras is measured using the KP index, which ranges from 0 to 9. A KP of 0 means very quiet magnetic conditions, while a KP of 9 indicates an extreme geomagnetic storm. For most locations in the auroral zone, you need a KP of at least 3 or 4 to see auroras. However, during major storms with KP values of 7 or higher, auroras can be visible at much lower latitudes. There have been historical records of auroras being seen as far north as the equator during extreme events, though these are exceptionally rare. The most powerful geomagnetic storm in recorded history was the Carrington event of 1859, which produced auroras visible in tropical regions and caused telegraph systems around the world to fail. Now, where can you actually see the southern lights? Unlike the northern lights, which can be viewed from populated areas in Scandinavia, Canada, and Alaska, the southern lights present a unique challenge. The auroral oval in the southern hemisphere passes mostly over the Southern Ocean and Antarctica, with only a few landmasses reaching into the zone. Tasmania, the southernmost part of Australia, offers some of the best accessible viewing opportunities. The southern tip of New Zealand's South Island, particularly around Stewart Island and the Otago region, also provides excellent vantage points. In South America, the southern regions of Chile and Argentina, including Tierra del Fuego and parts of Patagonia, occasionally experience auroral displays. The Falkland Islands, South Georgia, and other sub-Antarctic islands also sit in favourable positions for aurora viewing. Antarctica itself offers the most consistent aurora viewing, but obviously it's not easily accessible to most people. Research stations on the continent regularly observe spectacular displays, and scientists stationed there have captured some of the most stunning auroral photographs ever taken. The McMurdo Station, operated by the United States, and other research facilities provide valuable data about auroral activity throughout the year. During the Antarctic winter, when the continent is plunged into months of darkness, auroras become a regular fixture in the sky for those brave enough to endure the extreme conditions. Let's consider the best times to see the southern lights. Many people assume you need to travel during the southern hemisphere's winter, but that's not entirely accurate. Auroras occur year-round, but you need darkness to see them, which means the prime viewing season runs from March to September, when nights are longest in the southern hemisphere. The equinoxes, around March and September, are particularly favourable times because of something called the Russell-McPherron effect. During these periods, the orientation of Earth's magnetic field relative to the Sun's magnetic field creates conditions more conducive to geomagnetic storms. Within a single night, the hours around midnight tend to be most active, though auroras can appear at any time once it's dark enough. Weather plays a crucial role in aurora viewing, perhaps even more so than solar activity. You can have the most intense geomagnetic storm imaginable, but if clouds cover the sky, you won't see anything. Clear, dark skies away from light pollution are essential. This is one reason why Tasmania and New Zealand's South Island are such good viewing locations. They offer relatively accessible areas with low light pollution and frequent clear nights. Checking weather forecasts and aurora predictions together gives you the best chance of success. Various apps and websites provide aurora forecasts based on solar wind data and magnetic field measurements, allowing potential viewers to plan their observations. The speed at which auroras move can be quite surprising. When you watch time-lapse videos of auroras, they appear to dance rapidly across the sky, but in real time, their movement is often more subtle. The curtains and bands of light can shift and pulse over the course of minutes, with some movements happening faster than others. During intense storms, auroras can flicker and change very rapidly, with waves of light rippling through the display at what seems like incredible speeds. However, these movements are actually quite complex. What we're seeing is the changing pattern of particle collisions in the upper atmosphere as the solar wind interacts with Earth's magnetic field in dynamic ways. Auroras make sounds, though this remains one of the more mysterious aspects of the phenomenon. For centuries, indigenous peoples in both the northern and southern hemispheres have reported hearing sounds associated with auroras, describing them as crackling, hissing, or whooshing noises. Scientists were skeptical of these reports for a long time because auroras occur at altitudes where the air is too thin to conduct sound waves to the ground in the traditional sense. However, recent research has provided a possible explanation. During geomagnetic storms, the Earth's magnetic field fluctuations can cause a buildup of electrical charge near the ground, particularly on the surface of objects like trees or buildings. When these charges are released, they create the crackling sounds people report. This explanation is still being studied, but it suggests that what people are hearing is a real phenomenon, just not sound travelling directly from the aurora itself. The Southern Lights have played a role in the mythology and cultural beliefs of various peoples. The Maori of New Zealand traditionally viewed auroras as fires lit by ancestors or as reflections of torches carried by spirits travelling to the sky realm. In some Aboriginal Australian traditions, auroras were seen as dancing spirits or gods. These cultural interpretations remind us that long before we understood the physics behind auroras, humans looked up at these lights and tried to make sense of them through story and metaphor. The emotional impact of seeing an aurora remains the same, whether you're viewing it as a spiritual phenomenon or as the result of solar wind interactions. There's something primal about witnessing lights dancing in the sky that transcends scientific understanding. Photography has revolutionized our ability to capture and share auroral displays. The human eye and camera sensors perceive auroras differently. Cameras, especially those capable of long exposures, can capture colours and details that might appear more subtle to the naked eye. A display that appears as a faint greenish glow to an observer might photograph as vivid curtains of green and purple. This doesn't mean the cameras are lying exactly, but they're accumulating light over several seconds or even minutes, revealing structure and colour that our eyes, which process light in real time, might miss. Modern smartphone cameras have become increasingly capable of capturing auroras, though dedicated cameras with manual exposure controls still produce the best results. To photograph auroras effectively, you need a camera capable of manual exposure settings, a sturdy tripod, and ideally a wide-angle lens. Settings typically involve a high ISO, around 1600 to 3200, an aperture as wide as your lens allows, often f2.8 or wider, and exposure times between 5 and 25 seconds. The exact settings depend on the brightness of the aurora and the ambient light conditions. Too long an exposure, and you'll blur the aurora's movement and structure. Too short, and you won't capture enough light to show the display. Finding the right balance takes experimentation. Focusing in the dark can be challenging. So many photographers focus on a bright star or distant light source, then switch to manual focus to lock it in. The electromagnetic energy associated with auroras can affect technology in interesting ways. During intense geomagnetic storms, the fluctuating magnetic fields can induce electrical currents in long conductors like power lines, pipelines, and even railway tracks. These geomagnetically induced currents, or GICs, can damage transformers in power grids and cause widespread blackouts. The 1989 Quebec blackout was caused by a geomagnetic storm that induced currents in the power system, causing it to collapse and leaving millions without electricity for up to 9 hours. Satellite systems are also vulnerable. The increased radiation and atmospheric expansion during storms can affect satellite orbits and damage sensitive electronics. GPS accuracy can degrade, and radio communications can be disrupted. Airlines take auroral activity seriously, particularly for high-latitude routes. During strong geomagnetic storms, polar routes may be adjusted or avoided because the storms can interfere with radio communications and expose passengers and crew to increased radiation levels. At cruising altitude, there's less atmospheric protection from solar radiation, and during major solar storms, this exposure can increase significantly. The radiation doses are still small, but airlines prefer to minimize exposure when possible. Pilots flying in auroral regions are trained to watch for auroras as they can indicate an increased radiation levels and communication difficulties. The study of auroras has a long and fascinating history. Early scientists struggled to explain what they were seeing. Some thought auroras were reflections of sunlight off polar ice. Others proposed they were electrical phenomena related to the Earth's magnetic field. It wasn't until the space age that we really understood the solar wind and its interaction with Earth's magnetosphere. Christian Birkeland, a Norwegian scientist, was one of the pioneers in aurora research. In the early 1900s, he conducted experiments showing that electron beams directed at a magnetized sphere could produce aurora-like glows. His work laid the foundation for our modern understanding, though many of his ideas weren't fully accepted until decades later, when satellites could directly observe the solar wind and magnetosphere. Space-based observations have transformed aurora science. Satellites positioned between the Sun and Earth continuously monitor the solar wind, providing advance warning of incoming storms. Other satellites observe auroras from above, capturing images of the complete auroral oval and measuring the particle precipitation. The IMAGE satellite, launched in 2000, provided unprecedented views of Earth's magnetosphere and auroral activity. Ground-based instruments complement these space observations. Networks of magnetometers measure magnetic field variations, while specialized cameras and radars study auroral structure and dynamics. All sky cameras capture images of the entire visible sky every few seconds, allowing researchers to track auroral motion and morphology in detail. Auroras occur on other planets too, not just Earth. Any planet with a magnetic field and an atmosphere can theoretically produce auroras. Jupiter has incredibly powerful auroras, far more energetic than Earth's. These Jovian auroras are powered not just by the solar wind, but also by volcanic material ejected from Io, one of Jupiter's moons. Saturn, Uranus, and Neptune all have auroras as well. Even Mars, which has only a weak localized magnetic field, can produce auroral displays. These occur where ancient magnetic fields are frozen into the crust, providing localized regions where solar wind particles can interact with the atmosphere. Studying auroras on other planets helps us understand the fundamental physics of plasma interactions with magnetic fields and atmospheres. The structure of auroras is far more complex than simple curtains of light. Auroras can form arcs that stretch across the sky, often aligned roughly east-west. These arcs can be thin and discrete, or diffuse and spread out. Pulsating auroras switch on and off rhythmically, with periods ranging from seconds to minutes. Corona auroras appear when the observer is directly underneath the aurora, with rays seeming to radiate from a point overhead, created by perspective as parallel auroral rays appear to converge. Omega bands are large-scale structures shaped like the Greek letter omega, extending across vast areas of sky. Each of these structures tells us something about the processes occurring in the magnetosphere and upper atmosphere. The height at which auroras occur is surprisingly consistent. Most auroral light comes from altitudes between 100 and 300 kilometers, with the most intense activity typically around 100 to 150 kilometers. This is where the atmosphere is thick enough for frequent particle collisions, but thin enough that the atoms can remain in excited states long enough to emit light. Below about 90 kilometers, the atmosphere becomes too dense, and collisions between atoms happen so quickly that excited atoms don't have time to emit light before being bumped again. Above about 400 kilometers, the atmosphere is so thin that collisions become rare. The red auroras produced by high-altitude oxygen occur at these greater heights, where collisions are less frequent. Auroral research has practical applications beyond just understanding a beautiful phenomenon. The same processes that create auroras, the interaction between the solar wind and Earth's magnetic field, affect our technology-dependent society. Understanding space weather helps us protect power grids, satellites, and communication systems. Forecasting geomagnetic storms is similar in some ways to forecasting regular weather, involving computer models that simulate how disturbances from the sun will interact with Earth's magnetic environment. These forecasts help utilities prepare for potential problems, allow satellite operators to take protective measures, and inform airlines about polar route risks. The economic impact of severe space weather events could be enormous. A 2008 report by the National Academy of Sciences estimated that an extreme geomagnetic storm could cause up to $2 trillion in damage to infrastructure and take years for full recovery. This might sound alarmingly high, but it reflects our dependence on electrical systems and satellites. The more interconnected and technology-dependent we become, the more vulnerable we are to space weather. This vulnerability has led to increased investment in space weather monitoring and forecasting, with multiple satellites now dedicated to observing the sun and the solar wind. Indigenous knowledge about auroras often included the idea that they shouldn't be mocked or made fun of. In some cultures, whistling at the lights was thought to invite them closer or provoke them, which could be dangerous. While we now understand that auroras pose no direct threat to people on the ground, there's something interesting about this traditional caution. It reflects an understanding that auroras were associated with powerful forces beyond normal human experience. In a sense, that understanding wasn't wrong. Auroras are associated with powerful magnetic storms that can affect technology and represent the ongoing interaction between Earth and the Sun. The question of whether animals can see or react to auroras is intriguing. Many animals see differently than humans, with some able to perceive ultraviolet light, or with much better night vision. Do animals notice when the sky lights up with green and red curtains? There's limited research on this, but anecdotally, some people have reported unusual animal behavior during auroral displays. Reindeer in northern regions, for instance, are known to be active during auroral periods, though this might simply be because they're active at night generally. Birds that navigate using magnetic fields might be affected by the magnetic disturbances that accompany auroras. The reality is we don't fully know how animals experience these events, or whether they pay them any attention at all. time-lapse photography has revealed patterns in auroral behavior that are difficult to observe in real time. Over the course of a night, auroras might start as a faint glow on the horizon, develop into active bands and curtains, reach a peak of activity, and then fade back to a glow before disappearing entirely. This pattern reflects the evolution of the geomagnetic storm driving the display. As the disturbance in Earth's magnetic field develops, intensifies, and then recovers, the auroral activity follows suit. Multi-night time lapses during auroral storms show how the displays can vary from night to night, even though the same overall storm is continuing. The exact position and intensity depend on the specific configuration of the magnetic field at any given moment. Citizen science has become increasingly important in aurora research. Programs like Aurora Australis allow people to report auroral sightings in real time, creating a crowdsourced map of auroral activity. These reports help scientists verify and calibrate their models and instruments. They also provide data on auroral visibility at lower latitudes, where permanent monitoring stations might not exist. In the southern hemisphere, where the inhabited areas within the auroral zone are limited, citizen observations are particularly valuable. Every photograph, location report, and description adds to our understanding of how auroras behave and where they can be seen. The difference between the northern and southern lights is often asked about. Are they identical? The answer is complicated. In theory, they should be mirror images of each other because they're caused by the same solar wind interacting with opposite poles of Earth's magnetic field. For many years, scientists assumed they were indeed identical. However, detailed comparisons using satellite observations have revealed subtle differences. The asymmetry in Earth's magnetic field, along with factors like seasonal differences between hemispheres and the different distributions of land and ocean, can lead to slight variations in the auroras at any given moment. Over long periods, though, they remain fundamentally the same phenomenon. Light pollution poses a significant challenge to aurora viewing. The same glow that makes cities visible from space makes the night sky much brighter, washing out fainter auroras. To see auroras well, you need dark skies, which usually means travelling away from urban areas. This is one reason why aurora tourism has developed in regions like Tasmania and southern New Zealand. These areas offer dark sky sites within reasonable travelling distance. The growth of LED street lighting has actually worsened light pollution, in some ways because LEDs emit more blue light, which scatters more effectively in the atmosphere and brightens the sky more than older sodium vapor lights. Fortunately, there's growing awareness of the need to preserve dark skies, and some communities are adopting lighting ordinances to reduce light pollution. The speed of solar wind varies considerably. During quiet periods, it might travel at 300 to 400 kilometers per second. But during solar storms, particularly those following coronal mass ejections, speeds can reach 800 to 1,000 kilometers per second or even higher. Faster solar wind carries more energy, and when it impacts Earth's magnetic field, tends to produce more intense geomagnetic storms and brighter auroras. The solar wind isn't uniform either. It contains regions of different density and magnetic field strength, and these variations affect how it interacts with Earth's magnetosphere. When a high-density region arrives, it can trigger sudden bursts of auroral activity. Educational programs about auroras serve multiple purposes. They teach physics and space science in a visually engaging way that captures people's imagination. Students learning about electromagnetism, atomic physics, and the solar-terrestrial connection find auroras to be a tangible example of these concepts. Many schools in areas where auroras are visible incorporate them into science curricula, sometimes organising viewing events when forecasts predict active displays. Online resources, including real-time auroral cameras and forecasting tools, allow students anywhere in the world to follow auroral activity and learn about space weather. The connection between auroras and the Earth's magnetosphere is fundamental. The magnetosphere is the region around Earth dominated by our planet's magnetic field. It's shaped like a teardrop, compressed on the side facing the Sun and stretched out on the opposite side. The solar wind flowing around the magnetosphere creates a boundary called the magnetopause on the sunward side, and a long tail called the magnetotail extending away from the Sun. Auroras are essentially windows into the magnetosphere's dynamics. When we see auroras brightening and moving, we're seeing the visible signature of energy and particles flowing through the magnetosphere. The magnetosphere stores energy from the solar wind and periodically releases it in what are called substorms, which cause sudden brightenings and expansions of the auroral oval. Have you considered how explorers and early Antarctic expeditions experienced auroras? For people like Ernest Shackleton, Robert Falcon Scott, and Roald Amundsen, auroras were a regular part of the Antarctic experience. These men, working in an era before we understood what auroras were, witnessed some of the most spectacular displays imaginable. Their journals contain descriptions of auroras, sometimes in poetic terms, sometimes simply noting their presence. For these explorers, auroras were both beautiful and mysterious, a reminder of the strange environment they had entered. They had no aurora forecasts, no understanding of solar cycles or magnetic storms. They simply watched the sky and wondered. The energy involved in auroral displays is substantial. A moderate auroral display might involve power levels of billions of watts, comparable to a large city's electrical consumption. Major auroral storms can involve trillions of watts of power being dissipated in Earth's upper atmosphere. This energy heats the atmosphere, causing it to expand, which increases drag on satellites in low Earth orbit. During major storms, this atmospheric expansion can be significant enough that satellites need to adjust their orbits to compensate. The heating also creates winds in the upper atmosphere, moving gases around and changing the atmosphere's density structure. Aurora tourism has become an industry in some regions. While the southern lights are less accessible than their northern counterparts, certain locations have developed infrastructure to serve aurora watchers. Specialized tours operate in Tasmania, offering guided trips to dark sky locations with photography instruction and aurora information. In New Zealand, accommodation providers in southern regions market themselves to aurora enthusiasts. This tourism brings economic benefits to remote areas, though it also requires managing expectations. Unlike some northern locations where auroras are visible most clear nights during winter, southern lights viewing is less predictable from accessible locations, which means tourists might visit and see nothing despite clear skies. The relationship between solar activity and auroras isn't perfectly straightforward. It's not simply a matter of more solar activity equaling more auroras. The orientation of the magnetic field in the solar wind matters enormously. When the solar wind's magnetic field points southward, opposite to Earth's northward pointing field at the equator, magnetic reconnection occurs. This process allows solar wind energy to enter the magnetosphere much more efficiently. A strong but northward-oriented magnetic field in the solar wind won't produce intense auroras, while a weaker southward field can trigger major storms. This is why aurora forecasting involves monitoring not just the speed and density of the incoming solar wind, but also its magnetic field orientation. Auroral substorms represent one of the most dynamic aspects of auroral behavior. These are sudden releases of energy stored in Earth's magnetotail, the extended part of the magnetosphere, pointing away from the Sun. During a substorm, which typically lasts 1 to 3 hours, the auroral oval suddenly expands and brightens. Auroras that were confined to high latitudes push toward the equator. The motion and intensity of the lights increase dramatically. Then after the peak of the substorm, the auroras gradually recover to quieter levels. Multiple substorms can occur during a single night, creating waves of activity. The physical processes driving substorms are still being actively researched, involving complex magnetic field reconfigurations and particle acceleration. Proton auroras exist alongside the more common electron auroras. When protons from the solar wind enter the atmosphere, they create auroras too, but these look different. Proton auroras tend to be more diffuse and are typically observed at ultraviolet wavelengths that our eyes can't see. Specialized instruments can detect them though, and they provide information about the energy and composition of particles entering the atmosphere. The proton auroras occur alongside electron auroras during active periods, adding to the complexity of the overall display. Most visual observers wouldn't distinguish between electron and proton contributions, but scientists studying auroral physics track both types carefully. The folklore around auroras persisting into the modern era is interesting. Even though we understand what causes auroras, they retain a sense of magic and mystery. People who witness a spectacular display often describe it as life-changing or spiritual, even when they fully understand the physics involved. This suggests that the human response to auroras goes beyond intellectual understanding. There's something about seeing the sky come alive with dancing colours that speaks to something deeper in us. Perhaps it's the reminder that we live on a planet in space, constantly bathed in the solar wind. Perhaps it's simply the beauty of it. Whatever the reason, auroras continue to inspire wonder in the 21st century, just as they did thousands of years ago. The practical challenge of staying warm while watching auroras in the southern hemisphere cannot be overstated. The best viewing locations, whether in Tasmania, New Zealand, or Patagonia, can be quite cold during the prime viewing season. Unlike the rapid trip outside you might make during summer to see a meteor, aurora watching often involves hours of waiting in the cold for a display to develop or intensify. Proper clothing is essential. Warm layers, windproof outer layers, insulated boots, gloves, and hats. Many experienced aurora watchers bring warm drinks in thermoses and portable chairs. The challenge is staying warm while keeping mobile enough to adjust viewing positions and camera equipment. Cold also affects camera batteries, draining them faster than normal, so bringing extras kept warm in inside pockets is wise. The question of whether auroras affect human health comes up occasionally. The charged particles that create auroras don't reach the ground. They interact with the atmosphere at altitudes of 100 kilometers and higher, far above where we live. So there's no direct radiation exposure from auroras themselves. However, the geomagnetic storms that cause auroras can have subtle effects. Some studies have suggested correlations between geomagnetic activity and things like heart attack rates or hospital admissions, though these studies remain controversial, and the proposed effects, if real, are small. The mechanisms that might link magnetic field fluctuations to human biology are not well understood. Most scientists are skeptical that geomagnetic storms have significant direct health effects, but research continues in this area. The colour saturation we see in auroral photographs sometimes creates unrealistic expectations. As mentioned earlier, cameras accumulate light over several seconds, revealing colours that might appear more subtle to the naked eye. A camera might show vivid greens and purples while your eye sees a whitish-green glow with hints of colour. This doesn't mean you won't see colour. Intense displays definitely show colour to the human eye, but it might not be quite as saturated as in photographs. Understanding this helps manage expectations. The experience of seeing an aurora in person, even if it's less colourful than the photos suggest, is still remarkable. There's a three-dimensionality and sense of motion that photographs can't fully capture. Solar astronomers monitor the sun constantly, tracking sunspots, solar flares, and coronal mass ejections. When a significant CME erupts, they can determine whether it's Earth-directed and estimate when it will arrive. This forecast gives us 1 to 3 days of warning before the associated geomagnetic storm begins. As the CME approaches satellites in position between Earth and the Sun, such as the DS-COVA satellite, provide measurements of the solar wind's actual properties. These measurements, taken about an hour before the solar wind reaches Earth, allow forecasters to refine their predictions. They can estimate how strong the resulting auroras might be and how far toward the equator they might extend. This system isn't perfect, surprises still happen, but it's remarkably effective. The duration of auroral displays varies widely. Some displays last only 15 to 30 minutes before fading. Others can persist all night, waxing and waning in intensity, but maintaining a presence in the sky for hours. Multi-day auroral storms can produce displays night after night, though each night's activity might differ in timing and intensity. During major solar storm events, the kind that occur every several years, auroras might be visible for a week or more, though not necessarily continuously. Predicting the duration of a specific display is difficult because it depends on how long the favourable solar wind conditions persist, which can change rapidly. Artificial auroras have been created experimentally. High-altitude nuclear tests in the 1960s produced artificial auroras as a side effect. The radiation from these explosions interacted with Earth's magnetic field and atmosphere in ways similar to natural auroras, creating glowing displays. These experiments, part of the Cold War's space race and weapons testing, were eventually banned by international treaty. More recently, scientists have created small-scale artificial auroras using ground-based radio transmitters to accelerate electrons in the ionosphere. These experiments help test theories about auroral processes in controlled conditions, though the resulting displays are much smaller and dimmer than natural auroras. Auroral research contributes to our understanding of plasma physics more broadly. Plasma, the fourth state of matter consisting of ionized gas, makes up more than 99% of the visible universe. Stars are made of plasma, as are nebulae and much of the interstellar medium. Earth's magnetosphere contains plasma, and the interaction between this plasma and the solar wind plasma creates auroras. By studying these interactions in detail, scientists learn about plasma behavior that applies to systems throughout the universe. The physics of magnetic reconnection, particle acceleration, and plasma waves studied in Earth's magnetosphere are relevant to understanding solar flares, stellar winds from other stars, and plasma dynamics in distant galaxies. The impact of climate change on auroral viewing is an interesting question. Climate change is primarily a lower atmospheric phenomenon, affecting weather patterns, temperatures, and precipitation. The upper atmosphere where auroras occur is much less affected. However, climate change could indirectly impact auroral viewing through changed weather patterns that might affect cloud cover and storm tracks. If certain regions become cloudier on average, that would reduce viewing opportunities even if the auroras themselves remain unchanged. Conversely, if some areas see decreased cloudiness, viewing opportunities might improve. These effects are highly regional and complex, making it difficult to predict how aurora viewing conditions might change over coming decades. The cost of aurora-related satellite infrastructure is substantial, but considered worthwhile. Satellites monitoring the sun, such as those in NASA's Solar Dynamics Observatory and SOHO missions, cost hundreds of millions of dollars each. The Discover satellite, positioned between Earth and the Sun to provide solar wind measurements, cost about $340 million. Ground-based monitoring networks add additional costs. Governments fund these systems because the information they provide about space weather has significant economic value in terms of protecting infrastructure and satellites. The cost of not having this information, being unable to forecast geomagnetic storms, would be far higher in terms of unexpected damage and disruption. Auroral science involves international collaboration. Scientists from around the world share data from satellites and ground stations, work together on research projects, and coordinate observation campaigns. Organizations like the International Space Environment Service facilitate this collaboration, providing standardized forecasts and alerts. The global nature of auroral research reflects the global nature of the phenomenon and its impacts. A geomagnetic storm affects the entire planet simultaneously, making international cooperation essential for understanding and predicting these events. The personal experience of seeing auroras varies significantly between individuals. Some people become emotional, moved by the beauty and the realization of witnessing something extraordinary. Others are more analytical, thinking about the physics and trying to spot different structures and colors. Many photographers become so focused on capturing images that they later realize they spent more time looking through a camera than directly at the sky. First-time aurora viewers often express surprise at how the lights move and change, having expected something more static based on photographs. The common thread in most accounts is a sense of privilege at witnessing something special. Future auroral research will likely focus on several areas. Better forecasting remains a goal, particularly improving predictions of auroral intensity and location more than a few hours in advance. Understanding the detailed physics of magnetic reconnection and particle acceleration in the magnetosphere continues to be important. The launch of new satellites with improved instruments will provide better data. The upcoming solar cycle, the 25th since records began in 1755, is expected to peak around 2025, providing researchers with opportunities to study major storms. Long-term monitoring will help us understand how solar activity varies over timescales longer than the 11-year cycle. The development of Aurora apps and real-time monitoring tools has democratized access to auroral forecasts. Anyone with a smartphone can now check the Aurora forecast, view real-time solar wind data, and receive alerts when auroral activity is expected. These tools have made Aurora watching more accessible, helping people time their viewing attempts. However, they've also led to some frustration when forecasts don't pan out as expected. Aurora forecasting is probabilistic and uncertain, especially at longer lead times. An alert that auroral activity is possible doesn't guarantee anything will be visible, particularly from lower latitude locations. Managing these expectations while still providing useful information is an ongoing challenge for those developing these tools. The question of whether we'll have auroras in the distant future depends on Earth's magnetic field. The field is generated by motion of liquid iron in Earth's outer core, and as long as this dynamo process continues, we'll have a magnetic field and thus auroras. However, Earth's magnetic field does change over time. It weakens and strengthens, and its poles wander. Every several 100,000 years, on average, the field reverses completely, with north and south magnetic poles swapping positions. During these reversals, which take thousands of years to complete, the field becomes more complex and generally weaker. Would auroras still occur during a reversal? Almost certainly, though they might be more widely distributed around the planet rather than concentrated at high latitudes. Looking millions of years into the future, as long as Earth's interior remains hot enough to drive the dynamo, we should continue to have a magnetic field and auroras. The comparison between viewing auroras from the ground versus from space is fascinating. Astronauts aboard the International Space Station frequently observe auroras from above, looking down on the glowing curtains from orbit. From this perspective, the scale of auroras becomes apparent. What looks like a curtain stretching across the sky from the ground is revealed as a band wrapping around the polar region. The ISS orbit sometimes takes it directly through auroral displays, with the station passing through the ionosphere at the same altitude where auroras occur. Astronauts have described seeing auroras both below and around them during these passes, a perspective few humans will ever experience. The photographs they capture from space show the aurora's relationship to Earth's curvature and the planet's limb, providing a unique view of this phenomenon. Historical records of unusual auroral sightings provide valuable data for understanding long-term solar activity. Before modern instruments, the only way to track geomagnetic storms was through human observations of auroras. Records from ship logs, missionary journals, and newspaper accounts document auroras seen at unusual latitudes during major storms. In the southern hemisphere, these historical records are sparser than in the north, simply because fewer people lived at southern latitudes where auroras were common. However, records from Australian colonies, New Zealand settlements, and ships sailing southern waters have been compiled by researchers. These historical accounts help extend our knowledge of solar activity back before the space age and even before systematic scientific monitoring began. The role of Earth's atmosphere in creating the auroral colours cannot be overstated. Without an atmosphere, we wouldn't see auroras at all. The incoming charged particles would simply hit the surface, or, in the case of a planet without a magnetic field, be absorbed by the upper layers of whatever gas surrounds it. Earth's specific atmospheric composition, about 78% nitrogen and 21% oxygen with trace amounts of other gases, determines the particular mix of colours we observe. A planet with a different atmospheric composition would produce auroras of different colours. This is seen on other planets. Jupiter's auroras appear blue and purple due to hydrogen emissions. If Earth's atmosphere were significantly different, our auroras would look different too, though the underlying physics would remain the same. Auroral substorms follow a characteristic pattern that scientists have studied extensively. The substorm begins with a growth phase, during which energy accumulates in the magnetotail as the solar wind compresses the magnetosphere. During this phase, which can last from 30 minutes to a few hours, the auroral oval might brighten slightly, but activity remains relatively quiet. Then the expansion phase begins suddenly, with a dramatic brightening and poleward expansion of the aurora. This phase lasts 15 to 30 minutes and represents the main energy release. Finally, the recovery phase occurs over 1 to 2 hours as the system relaxes back to a quieter state. Multiple substorms often occur in sequence during a geomagnetic storm, creating waves of auroral activity throughout the night. The prediction accuracy for auroral forecasts has improved significantly over the past few decades, but still faces limitations. Short-term forecasts, made once solar wind data from upstream satellites is available, are fairly accurate for predicting the next few hours. Forecasters can see the solar wind properties about an hour before it reaches Earth and make reliable predictions about whether auroral activity will increase. Longer-term forecasts, days in advance based on observations of CMEs leaving the Sun, are less certain. The CME might not arrive when expected, it might be weaker or stronger than predicted, or its magnetic field might have an orientation that doesn't efficiently transfer energy to the magnetosphere. These uncertainties mean that aurora forecasts several days out should be taken as possibilities rather than certainties. Auroral beads are a particularly interesting phenomenon that occurs just before auroral breakup. These are small-scale wave-like structures that appear along an auroral arc, making it look like a string of pearls. The beads typically appear during the late growth phase of a substorm, immediately before the onset of the expansion phase. They're created by instabilities in the plasma sheet of the magnetotail. Observing auroral beads can be a sign that a major brightening is about to occur, making them of interest to both scientists studying substorm dynamics and aurora watchers hoping to see an intense display. The auroral electrojet is an electrical current that flows in the ionosphere during auroral activity. This current, which can carry millions of amperes, flows westward in the evening sector and eastward in the morning sector of the auroral oval. The electrojet is responsible for many of the ground-level effects of geomagnetic storms. It creates magnetic field perturbations that are measured by magnetometers and induces currents in long conductors like power lines. The strength of the electrojet correlates with the intensity of auroral displays, with stronger jets associated with brighter auroras. Ground-based magnetometer networks can map the electrojet's location and intensity, providing real-time monitoring of auroral activity even when clouds prevent visual observations. Black auroras are regions of darkness within an otherwise bright auroral display. Rather than being areas where nothing is happening, black auroras are actually regions where upward-flowing electrons are present. While downward-flowing electrons create the visible auroral light, upward-flowing electrons indicate a different part of the magnetospheric current system. These dark regions can appear as curls, fingers, or patches within bright auroras. They're particularly noticeable during intense displays when the surrounding aurora is very bright, making the dark regions stand out by contrast. Black auroras represent an important aspect of the auroral current system that's easy to overlook if you're only paying attention to the bright parts. The question of whether augmented reality will change how we experience auroras is worth considering. Already, some apps can overlay information on a smartphone camera view, identifying constellations or showing auroral forecasts. Future AR systems might provide real-time identification of auroral structures, display magnetic field lines, show the connection between ground features and overhead auroras, or even simulate what an aurora would look like if it were more intense. While some might argue this detracts from the pure experience of observing nature, others might find it educational and enhancing. The technology could make aurora watching more accessible to people who are uncertain about what they're seeing or want to learn more as they observe. The thermal effects of auroral precipitation extend beyond just heating the atmosphere. The influx of energy causes the atmosphere to expand, as mentioned earlier, but it also drives winds and creates density irregularities. These effects influence radio wave propagation, affecting communications and GPS signals. They also create turbulence at the boundary between the upper and lower atmosphere. The heat deposited by auroral particles eventually works its way down through the atmosphere, though by the time it reaches the surface, it's negligible compared to solar heating during the day. Still, the upper atmosphere can warm significantly during major auroral storms, with temperature increases of hundreds of degrees at altitudes above 200 kilometers. Auroral chorus is a type of electromagnetic wave generated during auroral activity. These waves, in the very low frequency range, sound like birdsong when converted to audio frequencies that humans can hear. They're created by the same energetic electrons that produce visible auroras. Auroral chorus propagates along magnetic field lines and can accelerate electrons to very high energies, contributing to radiation belt populations. Ground-based radio receivers can detect auroral chorus, allowing researchers to study auroral processes even when the aurora itself isn't visible. Some aurora enthusiasts use radio receivers to listen to auroras, adding an auditory dimension to the experience. The impact of artificial satellites on auroral research has been transformative. Before satellites, scientists had to infer what was happening in the magnetosphere based on ground observations of auroras and magnetic field variations. Satellites have allowed direct measurement of the solar wind, the magnetosphere's structure, particle populations, electric and magnetic fields, and plasma waves. This has revolutionized understanding. Constellations of satellites, multiple spacecraft flying in formation, can measure how structures in the magnetosphere evolve over time and space. Mission clusters, like Themis and Cluster, have provided insights into magnetospheric processes that would have been impossible to obtain otherwise. Auroral kilometric radiation is a type of radio emission generated by auroral processes. This radiation, at frequencies around 100 to 400 kHz, is produced by electron beams in the auroral region. It's called kilometric because of the wavelength, which is in the kilometer range for these frequencies. AKR is one of the most intense natural radio emissions in the solar system. Earth emits about 10 million watts of radio power via AKR during active periods. This radiation propagates out into space and can be detected by spacecraft far from Earth. It's been used as a remote sensing tool to study auroral activity from distant vantage points. The poetic and artistic responses to auroras throughout history form an interesting cultural thread. Painters have attempted to capture auroras, though the medium of paint struggles to convey the motion and ethereal quality of the lights. Photographers have been more successful in recent decades. Writers and poets have used auroras as metaphors for the mysterious, the transcendent, and the sublime. In the Southern Hemisphere, these artistic responses are less numerous simply because fewer artists have had regular exposure to auroras. However, contemporary artists in Tasmania, New Zealand, and Patagonia increasingly incorporate southern lights imagery into their work, contributing to a growing cultural tradition. Citizen scientists have contributed to auroral science in ways beyond just reporting sightings. Amateur astronomers have photographed rare auroral phenomena, captured details that professional all-sky cameras missed due to timing or location, and even discovered new auroral features. The collaboration between professional scientists and dedicated amateurs has been productive. Amateurs bring enthusiasm, geographical coverage, and sometimes equipment and skills that complement professional efforts. Scientists benefit from data they couldn't collect on their own. This partnership exemplifies how modern science can engage broader communities in meaningful ways. The Southern Lights will continue to captivate humanity for as long as we're around to witness them. Each generation discovers them anew, experiences the same wonder, and asks the same fundamental questions about what's happening and why. While our scientific understanding has advanced tremendously, auroras remain in many ways as mysterious and awe-inspiring as they were to our ancestors. They remind us that we live on a dynamic planet in an active solar system. They show us that the universe is constantly interacting with our world in ways both visible and invisible. They inspire us to look up, to question, to understand, and perhaps most importantly, to feel a sense of wonder at the natural world. And with that, we've journeyed through 97 facts about the Southern Lights. From their fundamental physics to their cultural significance, from viewing tips to scientific applications, we've explored this remarkable phenomenon from many angles. The next time you have the opportunity to witness the Aurora Australis, whether from Tasmania, New Zealand, Patagonia, or anywhere else, the lights might grace the sky, you'll have a deeper appreciation for what you're seeing. You'll know about the solar wind travelling millions of kilometres to reach Earth, about the magnetic field lines guiding particles into our atmosphere, about the oxygen and nitrogen atoms releasing photons as they return to their ground states. But hopefully, you'll also simply watch and wonder, allowing yourself to experience the beauty without analysis, to see the lights dance and feel that ancient human response to something extraordinary occurring in the heavens above. Thank you for watching, and may your skies be clear when the southern lights come calling.